As I mentioned in one of the earlier lectures, basically what we're doing is a random walk through vector calculus and vector integral theorems, kind of compressed into just a few lectures. So things are going to go in different orders. I'm going to, as usual with the theme for this course, I'm going to try and highlight the physics whenever it's relevant. I'm also going to try and highlight the technique when it's a technique that gets used a lot. When it comes to the proofs, most of the time I'm going to do enough of the proof to show you, convince you that there is something there, but maybe not the full, all the steps and all the algebra and all the proof, because hopefully you've seen that in other places. So the first thing we're going to do is we're going to start with two-dimensional situations, and we're going to look at what's known as Green's theorem. Now, one nice thing I can tell you right now, I can never remember any of the names of all of these things. So when it comes time for the test, it's not like I'm going to say, use Green's theorem to do this, or use Gauss's theorem or Stokes. It's useful to know the names if you can. But what's key is to know all of these principles and just be able to use all of them. And like I said, I'm going to try and give you some hints to remember. Green's theorem really is a special case of ones we'll do later. We'll see that as we go on. And it focuses on things in the plane. So we'll have a curve, which is the boundary to some area A. And we have the area A that's bounded. Now, one thing to keep in mind, because we're confining ourselves initially to the plane, this area A really is the obvious flat area bounded by that curve. When we come to 3D, I mean, you have to imagine that area, that curve, I'm sorry, can bound a whole bunch of infinite areas that come out of the plane. Just think of a windsock. If you know what that is, you know the things that they use at airports to tell which direction the wind is, right? The edge of the opening is the boundary to a surface that can take on almost any shape. So I can pull this area out, and that curve is still the boundary to that area or that surface. Now, Green's theorem basically, as all of these will be, is something about the area. So if it's about the area, that's the region, so we need the derivatives. So notice that that's dA. I'm working explicitly in Cartesian coordinates here, and here's the derivatives, as we promised. The derivatives are the thing that go with the region, and then the boundary, we have P dx plus Q dy. Now, this one looks a little bit different. Because we're explicitly writing it here in component notations of P and Q. We do this because this actually combines two theorems in one. You'll see, depending how we define P and Q, this is a theorem about the curl or a theorem about the divergence. Right? Because in purely 2D, the curl only has one component, the z component. And this looks explicitly like a curl because it's a difference. Notice if I have P be minus the x component, the y component of some function, then the minuses cancel and this will look like a divergence. So we'll see that as we go on, that this contains two theorems. And that's why we break it up like this. And we have the separate pieces. So this side, we'll see, is really some other more general function f dotted into dr. And depending on how we define f, this will end up being a curl or a divergence. But the first step we want to do is kind of justify where this comes from. And almost all of these proofs have a similar feel or flavor to it. It's basically drawing the right set of things you're summing up. Because remember, integrals are all about summing stuff up. So imagine I have some curve. And I have the two maximal endpoints of the curve, A and B, in the x direction. Well, I can take slices, and in the y direction, there's the lower and the upper value of this slice. Now, if I look at the first piece, the dp dy, I can add up dp dy, whatever that function is, by doing the integral from a to b in the x direction, and then doing the integral from y lower to y upper. And I'm sorry, do this integral first, sum over my little strip, and then sum my strip. So this is the sum over the strip. So the first thing I do is I sum up from y lower to y upper. Once I get all these strips, I then sum over those, like that. So that's basically the fundamental definition of this area integral. So I want to make sure you have that picture in mind. And now, this integral, right, we know what dp dy is. Okay, its definition means that what we're going to get is the integral from a to b of p of x evaluated at y upper minus p of x evaluated at y lower dx. Right, that's the piece that's left. That's why we chose to do the y slices first, because basically our dy's cancel, right? The integral of dp dy is just p evaluated at the two endpoints. And so that's why we get this. Now, notice this is, we go for all of the upper and we go for all of the lower ones. Now, we can change our limits of integration on the upper one. And this is a common thing to do. Notice if I redraw my curve here, right, both of these are going from a to b. They're both going like that. What I really want is the integral around the curve. So to go around the curve, one of them has to go from a to b, and one has to go from b to a. Okay, so if I'm going to go from a to b, and then b to a, and I want to do it in my standard counterclockwise direction. This is the convention. So the upper one is what we switch. And it just turns out that this is kind of our right-hand rule-ish idea. And so by switching, we get a minus sign, and so I have minus the integral from a to b of p of x y lower dx minus the integral from b to a of p x y upper dx. But that is just the definition of going on the curve. That's what the line integral means. So this is just minus the integral on the curve of p of xy dx. Okay? And this was our integral of dp dy dx dy, that double integral over the area. So we see that's why there's a minus sign in the dp dy integral, this minus sign here. Now, what I'm going to do with a lot of these proofs is leave the other step for you to do. So to get our other piece, dq dx, to be q dy around the curve, of course now what are we going to do? What type of slices do we make if we want to do the dq dx? We now take our horizontal slices, because we're first going to do the integral dx, and that's going to give us just q evaluated on x, say, left and x right, however you want to call it. And now you'll find that you don't get a minus sign, that the correct side is the one that you switch, and we end up with the full expression we wanted, which was, I'll rewrite it here, And just remember a notational thing. The circle in the integral tells us it's a closed curve or surface. So you want to keep that notation in mind. Okay, I hadn't mentioned that at the beginning, right? We distinguish between integrals over curves that are just open curves and integrals over closed curves. Same thing with surfaces. So this little circle means closed. Any questions on that derivation? Because we're going to do a lot of things that look like that, a lot of adding up pieces, but I want to make sure that's kind of clear. Yeah?
If the integral of the partial q partial x dx is the horizontal and the p dp dy is the vertical, why are we summing the two?
No, okay. So notice this by itself does not give you the area integral. Right? We're summing the two. Right? We could have just said, oh, here's that rule, right? For a double integral of a thing that's a partial derivative with respect to y, we get that. And I think I see your question. And we could have done q separately, but we'll see that by putting them together, so we get to look at what happens to vector functions. So if you had a scalar function, right, then yes, the integral of p dx around the closed curve is the same as the gradient, the derivative of p in just the y direction. The integral of a scalar dy, okay, is just the integral in the x direction.
And we're not double counting them, because we did a partial derivative, so we wouldn't be.
Well, no, we did this whole thing, and we found out it was this piece of it. We did this whole thing, and we find out it's this piece of it. Notice there's a dx left, there's a dy left. Right? There are two separate area integrals that we did, and that's why we get two pieces here. And you could have just taken this separately or this separately if you wanted. But in a sense, what it's showing you is you have to be a little bit careful about your minus signs when you do it. Now, with this, there are two things we'd like to do with it. Okay? The first is let's consider the case, okay, where f of xy is p I hat plus q j hat. So this is just notation for f sub x. This is notation for f sub y. Okay? Then it's pretty easy to see, as I mentioned at the beginning, that f dot dr is just p dx plus q dy, which is exactly the right-hand side of the equation. So that's a line integral around a closed path. And then, the other side of it should be the derivative of that. And the derivative that we get, well, dq dx minus dp dy is just the curl of f, the z component of that. And if you notice, right, if I'm completely in the plane, then the area vector dA is z hat dx dy. And so what I really do have on the left is the curl of f, which is a vector, dotted in to dA, which is a scalar. So as I said, you can kind of figure out what vectors you need by making that argument. But we also get a second identity for free, because I can make q equal to vx and p equal to minus vy for some vector function v.
Wait, is that a semicolon or is that a
That's just a colon. How about there? 4.
After the V, that's not a G.
Oh, yeah, that's a semicolon.
Okay.
Yeah. Those are my two things. And now, right, if I work it out, dq dx minus dp dy is equal to dv sub x dx plus dv sub y dy, which is the divergence of v. And so now I have a relationship between the integral of the divergence of v dx dy is equal to an integral around the curve. Okay, in this case you have to be a little careful. It's not v dot dr. If you look at it, because of the minus signs, it's v dot n hat dr. Or if you just write it out, it's the integral around the boundary of the area, right, of minus vy dx plus v sub x dy. So if you remember the normal vector, right, you pick up a minus sign in the slope because you go the opposite way. And so you get that switching of things. So this is a little more subtle to see under our general rule, but it's basically an integral of a function. It's an interesting scalar. It's a slightly different thing than we've had before, and that's why over here you still end up a scalar, but you end up with a different derivative. And what we'll see, skipping ahead and thinking about, does anyone remember what divergence tells you about?
Flux.
Flux. So flux is about how much vector field is doing what? Passing through the surface. And so picking up the n hat makes sense here. Our surface is a line in this place. So it's a 2D surface and a 2D flux, which we're going to come back to and reiterate, because I can't say it enough.
And that curl dot dA is kind of the same thing, right? Because dA is also a roll.
Well, in the curl case, it's a little different, right? The curl, because we're in 2D, the normal in that case is just enforcing our right-hand rule to get the direction of circulation correct. Okay, so curl is about how your vector field moves around your area. Okay, and so it's this sort of circulation, and we see in the plane it looks like a flux because of that dA and everything, but it's really it's really your circulation vector. And the circulation is the amount that's kind of perpendicular to the plane that also happens to be what the area is perpendicular to the plane. So it's not quite the same idea as a flux.
But this isn't saying the curl, like the curl, because the curl vector is going to be where it's pointing towards your thumb, even though it's actually curling in the plane.
Right, exactly. Yeah, the curl vector is perpendicular to that.